Welcome to the Inspiring Sustainability Podcast. My name is Adam Woodhall, and today I am delighted to be inviting Melanie Windridge of Tokamak Energy. And so welcome, Melanie.
Hello, it's a pleasure to be here.
And Melanie is both a communications consultant for Tokamak and also a plasma physicist by training. And what does Tokamak do? Well, they specialize in nuclear fusion. So because nuclear fusion is still very much science fiction, and I'm guessing many of the listeners might not understand what it's all about, what we'll do is dive straight into understanding a bit about nuclear fusion, and then we'll talk a little bit more about it. So, Melanie, give us the headlines of what nuclear fusion is.
Well, nuclear fusion is the reaction that's happening in the sun and the stars all the time. So the reason that we have all that energy from the sun, the reason we can feel its warmth and it can grow our plants and everything that the sun does, that's all coming from nuclear fusion. That's what's creating that energy. And what's happening is small particles, the nuclei of atoms, are coming together to make larger atoms in the center of the sun. So hydrogen is joining together to make helium. And then later on, actually, helium can come together to make carbon and bigger atoms. So all of the atoms and the molecules that are in the universe are actually created in stars. And fusion is the basic process. So it's the energy process for the universe, if you like. And since scientists figured out what was causing the sun to burn, to create energy, they've been dreaming of harnessing this energy for use on Earth.
Great. So great ahead. So basically what we're doing is we're looking to create the conditions that are in the sun on Earth. Now, why? Because there is a reason why I've asked you to be on the Inspiring Sustainability podcast. There's actually quite a few reasons, but so because nuclear obviously has a bit of a bad reputation with some environmentalists. Not all of them actually, but some. So why is fusion something that's going to be potentially game changing, especially on the sustainability side of things?
Fusion is kind of the dream energy source because it produces huge amounts of energy for only a small amount of fuel. So as an example, the fuels that we would use on Earth are heavy types of hydrogen, so deuterium and tritium. And actually tritium comes from lithium, which everyone's familiar with because it's used in batteries, for example. And so just one laptop battery and half a bath of water from which you can extract deuterium is the equivalent in energy terms to about 40 tons of coal. So you can get huge amounts of energy from relatively little fuel, and also without taking a lot of space, because a lot of renewable energy sources, like, for example, solar panels or windmills, they're going to take large areas in order to generate the energy that we need. And this can be tricky in places where the energy demands are high, but the space is low, for example, cities. So fusion would be a great energy source for places like that where you've got high demand and low space, because you'll be able to get a lot of energy to satisfy that demand. But on top of that, it's clean, it doesn't produce any greenhouse gases, and it produces no long-lived radioactive waste either, because the reaction, deuterium and tritium, comes together to make helium and a neutron. And so helium is the main product of the reaction. Of course, helium is safe. So we're not producing any long-lived radioactive waste, which is a problem with fission. In fission, you're producing waste that will last maybe tens of thousands of years and need to be buried. Fusion doesn't do that. It does produce a little bit of radioactive waste in the structure of the power station itself. So it's not producing that waste in the reaction, but over the lifetime of a power station, its structure, the metal, will become slightly radioactive. But this is less of a problem because by careful choice of materials, we can actually minimize that radioactivity. And also, it won't last for tens of thousands of years. It will probably last for about 50 to 100 years before the radioactivity has decayed away and the materials are safe and able to be recycled. So it's a human timescale. It doesn't have that legacy, that burden on future generations. So I think that's very important for sustainability as well. So fusion is clean, green, safe, and it's abundant. So it's a really dream energy source for the future to satisfy our rising energy demands.
Yeah, definitely. Okay, so great. We've established the kind of why I would invite you onto in the big picture. So I'm just going to give some headlines to the listeners as to what else they can expect from today, because what has been nuclear fusion is famous for really two things in many senses. One, what we've just detailed, which is that it could be the energy source of the future. But also, it's been something that's been from basically the 1980s, something that's about 30 years away every time. So even now, if you go, there are other organizations which are looking to create nuclear fusion power plants, and they are still 30 years away. Now, what's interesting is Tokamak he's got a process which could kind of fast forward that much more quickly. And so we're going to be talking about that and how they as a much smaller organization are going to be able to get to that kind of promised land maybe within just over a decade or so. But also one of the things that's interesting for me is the journey of a small organization, how it's getting there. And then as an aside, we're going to be talking about Melanie a little bit about her and her journey as particularly as a woman in a very male dominated industry and it's with a very science fiction sort of training that you did as a plasma physicist. So actually let's start on that other kind of thing that nuclear fusion is famous for. Can you give a little bit of history going back to when they first started looking at fusion as being a potential energy source, as I say, back in the 20th century?
Okay, so fusion started being investigated more seriously after the Second World War. So there were experiments in the 50s that were looking at how using a plasma and how you could maybe confine this plasma. So a plasma is just an electrically charged gas, and it only exists when there's enough energy in the system to strip atoms apart. So electrons come away from the nucleus of the atom and then they move around separately. And so this plasma can conduct electricity because those electrons can flow through the gas and they conduct the electricity. So they started doing experiments with plasma in sort of donut-shaped rings, and they'd run a current through it, and they would see that it would sort of pinch together. It pulls itself together away from the walls, but they couldn't get to high enough temperatures like that because plasmas are very unstable. It would sort of twist up and kink, like if you were twisting an elastic band too much, and then it would just lose all its configuration and it just hits the walls and nothing happens. And so they realized that actually they were going to need to learn a lot more about this plasma state because they just didn't know very much about it at all. And so a lot of research then was in the early decades was done into better understanding plasma and basically how you can confine it or trap it, because that's essentially what you need to do. If you want to make the conditions that are in the center of stars, you need to get it hot enough for long enough for fusion reactions to occur. So you need to keep this turbulent, dynamic, hot gas, plasma, stable for many, many seconds before fusion reactions will kick in, and then hopefully keep the reaction going, keep the plasma hot. And so that's been the challenge for the last 60 years, actually, just controlling this plasma. And it's not dangerous. It's, if you lose control, it's not a big explosion or anything. It's just that the plasma cools. And in order to do fusion, to have those conditions that we see in the center of stars, we need temperatures of hundreds of millions of degrees. So that's pretty hot. So controlling the plasma is really about keeping it stable and keeping it away from the walls so that you can keep it hot because you have to get it hot enough for fusion reactions to occur. And so, yeah, there was a lot of research going on in the early years, just trying to understand plasma and trying to confine it and trap it. And in the 60s, the Russians came up with a concept which was called a tokamak. And this tokamak is basically a ring donut shaped machine with big magnets that go around the ring, as if you've got a solenoid wrapped round on itself, so a big curl of wire around a donut. And this tokamak is a way of trapping plasma, and it's the best system that we have so far for actually confining a plasma. And they were able to reach higher temperatures, and so the tokamak became popular around the world as a concept to investigate. And this is where Tokamak Energy came from. So about how long ago? At the end of, so about 2009 or 2010, Tokamak Energy span out of the Culham Centre for Fusion Energy, which is the main fusion laboratory in the UK. And we wanted to work on smaller tokamaks, actually. So using the tokamak concept and all of that knowledge that's built up over the years, but working with new technologies so that we can build smaller machines. I suppose that's something that we'll come on to a little bit later. But yeah, so the history of fusion is that, first of all, a lot of plasma and trying to understand plasma. The tokamak emerged as like the front runner, if you like. And then there was a lot of research. JET, the big machine in Oxfordshire called JET, which is a joint European torus. That's the best performing tokamak in the world so far. It started operating in the early 1980s, about 1981. And in the 1990s, it achieved fusion. And another machine in America did as well, TFTR. But so they got real fusion reactions. So it's not just science fiction. They've actually made fusion reactions. The one thing that they haven't done yet is get more energy out of the machine than they put in. And that's obviously important if you want to make a power station. But JET holds the world record for fusion energy out. So they produced 16 megawatts of fusion power, which was about 65% of what was put in. So that was in the 1990s. But since then, things have kind of slowed down a bit because the machines started getting bigger and bigger and bigger. And particularly, they started working on a big machine called ITER, which is being built at the moment in the south of France. And ITER is going to be huge. It's going to be probably, it's about 2 or 3 times the size of JET, and JET is sort of 12 meters high, I think. So it's going to be a really big machine, and that's not a bad thing in itself. ITER is an incredible engineering project. It's very, very impressive, but because it's so big, it became a worldwide collaboration, and it became very bureaucratically difficult, and it's been very much delayed. And so that's the thing with the fusion program now. We've been sort of waiting for the last 30 years for the next big machine, and it's sort of been slowing down the fusion program.
Yeah, and I think that's the interesting thing that with my kind of like schoolboy interest in science, unfortunately I gave up physics when I was about 16, but I still have a fascination with it as a kind of non-professional person, and that's the thing that it was. I'd heard about this. I didn't realise what the name was. The ITER, the one down in the south of France, and that it's kind of like trying to do things big and build that. And so because my understanding was back in the 80s there was actually an international collaboration, including Ronald Reagan and even, was it the Russians, looking at this? Or what was going back there? How did that start out?
Yeah, so ITER was, there were different ideas at the time, back then, and there still are actually. There are different ways of the tokamak is not the only way of achieving fusion conditions. But at the time, the tokamak was sort of the forerunner, and they decided that they wanted to build a bigger tokamak, and I think at the end of the Cold War, it also became symbolic. The tokamak is a Russian design, and they wanted to get together the Russians and the Americans and the Europeans as well, and do this thing for humanity. So solve the energy problem. So there was a meeting with Reagan and Gorbachev where they decided, they shook hands, they were going to make this big fusion machine, and so that was quite symbolic at the end of the Cold War. But then, as I said, it became very big and it became very bureaucratic. The idea for making it bigger is actually a sensible one, and it's based on the technology that was available at the time, because there are three main things that affect the fusion power that you get out of a reaction. One is the efficiency of the machine. One is the strength of the magnetic field that you're using to trap your plasma. And the other is the volume or the size of the machine. And if you increase any of those things, you're going to increase the fusion power. Actually, the magnetic field strength has the greatest effect. The efficiency of the machine has the next largest effect. And then the size, the volume. But at the time, and still today, the magnetic field is the more expensive part of the machine, and it's difficult to increase. With the magnet technology that was available, it limits the magnetic field you can get. So they found it hard to increase the magnetic field. The efficiency of the machines is also fairly fixed. With the Tokamak design, it had a sort of limited efficiency. And so the easiest thing to change, and the thing they had the most control over, was the size. And so that's why the machines were getting bigger and bigger. It was logical. The thing that's changed is that over the last 30 years, say, technologies have changed a lot. You can think about that. If you think about what you were using in the 80s or the 90s, like, for example, I often think about listening to my Walkman when I was a child in the 80s. Like, now we have music streaming and MP3s, and it's completely different. Technologies move on. And so magnet technologies have moved on as well. And now we can do things differently to how we could have done them 30 years ago. And this is what Tokamak Energy is investigating, because if we can use new technologies and increase that magnetic field, for example, and increase the efficiency if we can, we're looking at a slightly different shape of machine as well. So a spherical tokamak, which is like a more squashed up donut or an apple shape. If we can use these new technologies, then we don't need to increase the size so much. So we can bring the size of the machines down. And I'm not saying it's going to be tiny. It might still be the size of the jet tokamak, for example. But that's a big difference when it comes to building a machine. And if you can make as much of it as possible in factories, then that also reduces the cost and increases the time scale towards fusion. So the idea of the new technologies is really key.
Yeah, definitely. And just for that, by the way, for the listeners, for the nerds out there that want to do a bit more research, it's the International Thermonuclear Experimental Reactor, which understandably everybody calls the ITER instead.
And so they say that ITER means the way in Latin.
Ah, there you go. So there's a double sort of reason for ITER. And I think it's what's interesting for me is that because I'm passionate about kind of how you do things small and kind of start kind of a more of a startup mentality and as lean as possible, I think is really important. How is Tokamak Energy approaching this in a kind of with a kind of startup sort of lean mentality? Tell me a bit more about that.
So, as I said, they started in about 2009. Or 10. And the idea was then, we were mainly looking at using tokamaks as neutron sources, actually. So not necessarily focusing on energy. But by 2012, we had decided that actually we wanted to try and make power stations from these smaller tokamaks. And actually there was something happened there with the technologies, with the magnet technologies. So we use something called high temperature superconductors for our magnets, or at least we plan to in the future. We're still investigating them. And the high temperature superconductors got to a stage where you could actually use them to make magnets. So this superconductor is actually a ceramic, so like a china cup or something like that. So they had to establish the technology so that they could make this ceramic really, really thin and into tapes that you can then wind into magnets, like wrap around into coils. So when that happened and we realized that we could actually use this new material for new magnets, that's when Tokamak Energy sort of shifted and said, okay, let's really concentrate on working towards fusion power stations now. And sorry?
Yeah, so just as a bit of a contrast, when are they saying now with ITER that they think that might get some kind of more energy out of their plant than they're putting into it? And when is the time that you're looking to get the first commercial prototype for Tokamak Energy?
So we have targets on the way to fusion energy. So they're like little step-by-step goals. First of all, we wanted to firstly demonstrate our capabilities and demonstrate that you could use these high-temperature superconductors for magnets. We did that in 2015. We made a small tokamak with all its magnets made from high-temperature superconductors, and we ran it for over 24 hours to prove that technology. Now, there's still a lot of work that's going on in developing high-temperature superconductors for magnets, and that's something that we're doing in our magnet lab. But then at the same time, we're also working on building bigger tokamaks to increase our tokamak capability. So the next thing we wanted to do in a machine that we have called ST40, we want to get fusion temperatures. So we want to get to 100 million degrees in that machine. So far, we've achieved 15 million degrees, which is hotter than the center of the sun. So we did that in about May this year. So that was a really exciting milestone for us. And hopefully in the next year or so, we can achieve fusion temperatures, so 100 million degrees. And then after that, the next step is to put these technologies together, the tokamak and the high-temperature superconducting magnets, and hopefully generate more energy than we put in, so get past energy break-even. I'd like to see that happen before the middle of the next decade, preferably sooner, so sometime in the next 5 years. And then after that, we'll be demonstrating. We'll have to build a bigger machine that will demonstrate first electricity. So we have these targets. We'd like to demonstrate the commercial feasibility of fusion by 2030. So either making enough heat for electricity, even if we don't actually make the electricity, or making the electricity itself. So those are our plans. And then hopefully you could roll out power stations like from the 2030s. But of course, these are targets, but the timescale question is a really, really tricky one because it relies on so many things. And the science is one aspect of it. And of course, it's science. It's an exploration. We don't know what we're going to find. That's the thing. We can have our plans, but we don't know how tricky it's going to be. There might be new things coming up that we've never anticipated. That's the way science works. And so that makes it hard to predict. But there are other things as well that are outside of our control. For example, there's the political side of things. And I think for a startup, it makes it a little bit easier because we're smaller, we're more agile, we can make our own decisions quickly. We're not caught up in like government bureaucracy. But still, there will be things like sites to consider. There will be things like licensing, because we will have radioactive material on site, even if it's a much lower level than fission. There will still be licensing to consider. There's even things like health and safety because of magnetic fields. So you can't put a tokamak. We're in an industrial site at the moment, so they can be quite close to other people, but you can't be like right next door. So there are lots and lots of things to consider that are out of our hands. And this is the problem that ITER's had, actually. It's not the science necessarily that's been holding ITER back. It's all the other things. And so hopefully for the startups, because they're smaller and more agile, hopefully they can get round some of these other external issues faster. But that remains to be seen. So yeah, we have plans to demonstrate the commercial feasibility of fusion by 2030. But as I said, it's not all in our hands. No,
I totally understand. But just to give a bit of an understanding of scale, how many people are currently working for Tokamak Energy?
Currently, we have about 50 employees, I'd say. But we also have a lot of consultants who work with Tokamak Energy as well. In fact, I'm a consultant. I'm not a full-time employee. And we're very lucky to have lots of older consultants as well. So people who have worked their careers in the fusion industry with tokamaks like JET or with ITER, and they have huge amounts of expertise that they're now bringing to us because they want to see fusion happen, and they believe that Tokamak Energy is a good way to go about it.
Right. Okay. Yeah. And so, and then just as an idea, how many people, I guess, are working on the ITER project?
Oh, goodness. Well, there'll be hundreds, and it depends on what you're considering as well, because there'll be scientists who are doing work, but at the moment it's under construction. So they'll have huge construction teams putting ITER together as well, and the engineers and things. So yeah, hundreds and hundreds of people. Yeah.
So maybe, putting it all together, my guess is that you guys have got maybe a good dozens, whereas ITER might have even thousands in total. And I think that's one of the things that's very interesting for me, is that you could get ahead of the game for them, because effectively you're comparatively a fast-moving speedboat, whereas they're a bit of a slow-moving super tanker. And it's, not making them wrong. I'm sure they're doing their best, but as you say, they've got lots of things which are kind of going to slow them down, and that's why, as I say, it's been famous for that. Nuclear fusion has always been 30 years away, but from what you're telling us now, your aim and desire is it's going to be around about, say, 15 years away before it actually turns into something that's approaching reality.
Yeah, that's the plan. We need to get this done. As we know, we're already seeing the effects of climate change. Yeah. We're seeing extreme weather such as this summer's heat wave. There's been huge wildfires due to the dry conditions, and people are actually now able to attribute this to climate change. Scientists are doing things called extreme events attribution, where they can use climate modeling to see whether climate change has increased the likelihood of a particular event happening. And this extreme heat wave is definitely more likely because of climate change. And so it's getting more and more urgent. We don't have another 30 or 50 years to play with. We have to find a solution to the energy problems. And yes, we do have renewables, of course, but as I said earlier, for the increasing energy demand, and particularly for areas where there's high demand and low space, we need fusion. So we at Tokamak Energy, and I think in the fusion community at large, ITER as well, we all really, really want to see this happen. And so if we can speed it up in any way, then we should do. I would never say that ITER is a waste, because so much work has gone into ITER that we are now building upon. So it's still been a really useful project, and when it works, it will test other systems. And there's a lot of work that needs to go on, taking it from like the scientific lab experiment to a commercial fusion power station. There's a lot of work that still needs to be done, and we're building on all that work that's gone into ITER. But if we can now take this concept and modernize it and use new technologies which enable us to use factory production to make things quicker and build smaller machines that are more cost effective, then we should be doing that, and that's what we are doing. So
definitely.
Fingers crossed we can get there faster.
So, and I think one of the things is about this speed thing is also, you alluded towards it earlier. Do you have competition? Are there other smaller organizations which are looking to create commercial nuclear fusion quicker than ITER?
Yes, there are. There are various different companies, a lot of them in North America. But there's another one in the UK as well called First Light Fusion. They are using bubbles, actually, and trying to do something which is called inertial confinement fusion, which is where you compress the fuel to fusion conditions, as opposed to using big magnets to trap it for long enough. But there are other companies, startups in North America, for example, General Fusion in Canada, which again is using a different concept, not a tokamak. It's like a mixture of using magnetic fields and then also compression. There's another one called Tri-Alpha Energy in America, which is using, again, a completely different technology. They're looking at, they have a more linear machine, so a straight line machine, and it's almost like they blow smoke rings together, like two plasma rings that come together and merge. And then they try and hold them there for a while and fusion happens. So there are various different approaches. And I think that's a really good thing, actually, because firstly, it shows that there's a will to get fusion done. There are private investors, ordinary people, not governments, putting their money into fusion. And for me, that is really, really hopeful. And we need more of it. We need to increase investment, private investment in fusion, and increase awareness of the possibilities of this solution and the fact that it's not science fiction anymore. And there's an emerging fusion industry and people are investing in it, because the more investment and the more innovation we have, the quicker we will achieve fusion. Yeah. So for me, it's really positive that there are startups doing things. Of course, we feel that Tokamak Energy have an edge because we're building on all these decades of research, of course. But a lot of those other different concepts were kind of thrown out when the tokamak became superior, if you like, back in the 80s, because budgets were cut. And so they couldn't investigate all these different strands. The governments had to sort of close in on one, and they happened to close in on the tokamak. But there may still be merit in some of these other ideas that didn't get investigated. So now people are looking at those as well.
Yeah. And I think what's great is that obviously, whilst it might seem a good idea to get all these international governmental organizations kind of collaborating, there's actually a lot of power in the kind of competitive aspect of this. That obviously each one of all these organizations, British, American, etc., you're going to want to be the first ones to demonstrate the opportunity and first ones to demonstrate real kind of commercial opportunity. And so there's that tension creates opportunity for creativity. And so I think it's great to hear that you're kind of leading with that. And just one final thing before we just have a little understanding about Melanie and your experience in all of this is, are there any sort of criticisms just that people might level at fusion as a sort of a fuel source, as an energy source?
Oh yeah, I'm sure there are. The big criticism you hear all the time is it's never going to happen. Why are we wasting our money on something like this? We should be putting more money into developing renewables, which we already know work, etc. That's a big criticism. I disagree. I don't think that you should stop doing something just because it's hard. I think that the promise of fusion is immense, and like I don't think that things are impossible. I think that certainly not everything is impossible, and it's just a matter of solving the problems hurdle after hurdle, and the reward will be huge. So let's do this. But that's a big criticism. Other things, oh gosh, I don't know. You can go and look at any fusion article on the web, and you'll probably find a load of them in the comments below.
Yeah, but is there any environmental sort of criticisms of it? So obviously there's the practical one, which, as you say, I think we still need to kind of, because this isn't just about looking at the next decades, it's actually looking at the next centuries potentially. And this is something that's, if it works, could be the main fuel source of civilization into the 22nd century. But what about on the environmental side? Is there anything that environmentally is criticised for, or potentially criticised for?
Well, of course, as I mentioned earlier, there is some radioactive waste that's produced in the machine, so there will need the power stations will need careful decommissioning at the end of their life. One of the fuels, tritium, is also radioactive, but it's a low-level radioactivity. It's only got a half-life of about 12 years, 12 and a half years, so it decays away very quickly. It's also very light, it's hydrogen, so it doesn't, it escapes very quickly. But also it would be made in the machine from lithium. It wouldn't need to be transported anywhere or stored. So and it doesn't need to be processed. So the handling of it is much more simple. But you do have that radioactivity. And so you could say that is a problem, but every energy source is going to have its disadvantages. And so it's a matter of how we deal with them.
Yeah, sure, of course. Okay, great. So, So yeah, let's finish off last few minutes. Tell us a bit more about Melanie. What brought you to this sort of this role? Give us a bit more of your background and history.
Well, I got interested in fusion just after my undergraduate degree, which was in physics, and I was traveling the world. Actually, I was backpacking and not quite sure what I was going to do with my life. But I always loved physics. That's why I read physics at university. And at some point, I heard about fusion energy. I read about fusion energy, and I was kind of aware of climate change and environmental considerations at the time. And whilst I was traveling, I was doing things like hiking in the Himalayas and seeing how like glaciers and like the effects on glaciers. And I've been diving and learning about the coral reefs and bleaching and things like that. And so I was quite aware of the impacts of climate change. And so when I heard about fusion energy, I just thought, this is incredible. If we could do this, it's going to solve all our problems. I was also very aware of the fact that you need energy independence as well, and that fossil fuels were going to run out. So it wasn't just about climate change. It was actually about a solution for the future and just ensuring that we had enough energy. So I just thought fusion is going to solve all our problems. Like if we could do this, it would be wonderful. And so I started learning more about it. And in the end, I did a PhD in plasma physics working on fusion energy. And so that's how I got into it. I think, of course, as a student, I was young and naive and didn't realize it was going to take so long, even though it had taken however many, like 30, 40 years up until that point. But I just wanted to get it done, and I still just want to get it done. So that's what got me into fusion.
Right. Okay. And then because as you say, you're a consultant to Tokamak Energy. What else do you kind of get up to? I understand there's a few other strings to your bow.
Yeah, I guess I just like, I have an interest, I suppose, in exploration and this notion of achieving impossible things. So I got really interested in polar exploration and mountains and that kind of thing. And as a plasma physicist, I got very interested in the Northern Lights. So I wrote a book about the Northern Lights, which started off as like a little journey. I wanted to see the aurora, so I went. And then when I got there and I saw the Arctic, and I thought, this is an incredible place. I want to come here more. And wouldn't it be interesting to travel around a bit and learn more about the stories of the aurora, from the mythology and the folklore to how you get into the science. And as a plasma physicist, I could really look into the science in quite some depth, because it's the same physics that's happening in a tokamak. It's just in a very different context, and in a very, very beautiful context. So I got all involved in the Arctic and the aurora, which I love. I still love. I really enjoy going on trips like as an expert to see the aurora and sharing with people the stories of the aurora. So I kind of got into that. And then at the moment, I'm working on something to do with science in the mountains and how science and technology supports us in doing incredible things. Like climbing big mountains like Everest. So that's my current project. So I sort of do that on the side. I have this little personal projects that I do on the side, but they're all in the same themes. If you look at it, I've realized, now looking back, that the themes are sort of the same, even the fusion one. It's this notion of exploration and achieving the impossible. I quite like that.
Right, great. And so and one of the things, it's not seen as being impossible, but it's certainly more difficult for women in science because there's just so many more men, especially in the kind of hard sciences such as physics. What's been your experience being a female physicist?
I've been quite happy, to be honest. Yes, I'm in the minority, and I have been right since I started physics, undergraduate. There were probably maybe 20% of girls in my undergraduate degree, and it just gets less as you go up. But I don't know. It's never seemed to bother me. I just get on with what I'm doing. There are always enough women around that I don't feel alone, and I think that's the key to it. Definitely when I started my PhD, I was put on my own in an office with about 8 other guys. And I very quickly said, sorry, do you think you can move me somewhere? And they put me with another girl and another guy as well. But there's always, as long as you have support, if there are other females around, if there are other people to talk to, then I don't think it's a problem. And yes, of course, there are little issues along the way, but I think everybody has little workplace issues occasionally. Yeah. So I haven't found it a big deal. Maybe I take myself less seriously. Of course, you do get people, particularly when you're blonde and young, people don't really expect you to be a physicist. But I've had that all my life, so I'm pretty used to it, and I just get on with what I do, and I enjoy what I do, and I it hasn't really been too much of an issue for me.
No, that's great that you've got that sort of energy behind it, and you're not finding it as a particular issue, and you're being kind of very positive about it. And great stuff. Okay, then. So I really enjoyed this conversation. I'm hoping that the listeners have done as well. So before we go, what I'd like to do is just find out where we can find out more about Tokamak Energy and also Dr. Melanie Windridge. So where online are good places to find you guys?
So Tokamak Energy has a website, tokamakenergy.co.uk. They're also they're on Twitter. They're on LinkedIn, so you can go and find them. And we're on YouTube as well. We've got a big YouTube channel that I make videos for, with help, of course, but like lots of information about our staff and the work that we're doing and our plans. So do head over to YouTube and have a look at those videos. And if you want to find out more about me, I also have a website, melaniewindridge.co.uk. I'm on Twitter, Facebook, Instagram, so you can find me there and see what I've been getting up to.
Great stuff. Yeah. Okay. Great. Okay, then. So this has been really enjoyable conversation. And so I'm just going to finish off, give a quick summary of where people can find myself. Adam Woodhall will find me on LinkedIn and Twitter. And then also there's the Inspiring Sustainability website, which is inspiring-sustainability.com. And then you can go to your favorite podcasting app and find it by just typing Inspiring Sustainability in, and it will pop up there, and it will be great, obviously, if people subscribe to the this, because it's a regular podcast. So, Melanie, just wishing to say thank you so much for your time and passion and knowledge that you brought to this conversation. I hope it's inspired some people with this opportunity for not just what might be happening over the next decades, but maybe over the next centuries, about how we can be gaining energy way into the future. So thank you.
Thank you very much.
Goodbye.
Bye.